my name is McKenna, and today I'm going to talk to you about Newman projection. And Newman projection is basically how you represent a carbon-carbon bond and what is around the carbon-carbon bond to see which molecule is going to be the most stable out of all the different kinds you can do it. I'm going to talk to you guys first with the model kit because I feel that this is the easiest way to see it, and then later on we're going to talk about the different diagrams using the pictures. So we're going to be looking at this super simple ethane molecule. Just pretend this is hydrogen. I left this a different color so you guys can see when I rotate it how it goes around. So here is our carbon-carbon bond. We're going to turn it so you cannot see it because we're really just worried about these molecules to find out which is the most stable configuration. And there are two different types of ways to look at this when we're talking about the rotation. The first way is going to be staggered. So as you can see, all of the bonds do not line up. They're not in line with each other. And the second one, they are. This is called eclipsed. So as you can see, they're all in line. And so it looks like you're looking at the same thing all the way across. And the way Newman projections work is only one of the carbons is going to be rotated 60 degrees each time. And as you can see, it will go back and forth between staggered and eclipsed all the way around. And you can see which one is most stable by using these diagrams, and that's why I made this one different, so you can see that I'm only rotating this one. That's the only one that's moving around this molecule right now. I had a lot of trouble with this at the beginning of the year. This is one of the first things we covered, but it really took me a while to learn it because the pictures really don't help me a lot. I'm a very hands-on learner, so I used the model kit to make what I'm about to use, and then I can use it to rotate it around and see which one would be more stable, and then I can use the model kit to draw the models out. So one tool that really helped me is obviously the model kit. And then I would also in my notes color code the picture diagrams that we draw, which I will show you in a second when I do my example problem. And that really helped me keep track of which molecule I was rotating around. We are going to look at a butane molecule, and we're going to do the Newman projection between carbon 2 and carbon 3, which are the middle two right here. And I used this model kit to help me with my different formations that I have up here, and so let's take a closer look at that. But this is really what I used in order to get that by just rotating one of the molecules 60 degrees each time. As you guys can see, I left the molecules from the front carbon the same every time. So the CH3 is always at the top, and then the two that branch off from that, the two H's at the bottom, will remain there. And then the other carbon was the one that I rotated around, and it rotates around A to B to C to D to E to F. And you can see that it goes back and forth between staggered and eclipsed in all of these. I used these pictures of the Newman projection to predict the most stable and least stable configurations of it, as you can see, which is listed from top to bottom on the right. E is going to be the most stable. It's located in the bottom middle, and this is because it's staggered, which has less potential energy than the eclipsed configurations, and the two CH3s are the furthest apart that they can possibly be, so that is the most stable. A and C are both equal because the CH3s are equidistant in both of those, so those are equal, and those are the next most stable because they're also staggered and they're not super close to each other, so they're pretty stable too. F and D are also equal when it comes to the stability of them because they're exactly the same. The CH is just located on the left rather than the right in each one. B here is the least stable, which is obviously because the two CH3s are right behind each other, behind and in front of each other, and that is not very stable at all, so that one will be the least stable. And we're going to use this stability chart to make our potential energy graph. Here is our potential energy chart for this Newman projection. As you can see, the lowest potential energy is going to be the most stable, so that's E, and if you look at our listing on the right, you can see that E is supposed to be the most stable. Our least stable is B, and that corresponds to the right as well, because that one's so high up there. A and C are both equal, as you can see, with the next most stable. And if you look at 0 degrees and 360 degrees under the degrees of rotation, you can see that those are the same one. That's because we've made one full circle around our Newman projection, so it's back to the start. So this potential energy chart will just repeat after that. And then back to D and F, those are equal, and they are the second to least stable, so they're lower than B but higher than the rest of them. I really hope that this demo kind of helped you out a little bit. There's some other things I also struggle with in this class, one of them being chair configurations, and one way that I overcame that was using the model kit that has been really helpful to me this semester. And the final thing I've really struggled with is defining the difference between SN1, SN2, E1, and E2, just because there's so much information that goes into that. And to help me with that, I made a little chart that I keep in my notebook, and when I was confused, I could just refer to that to see the similarities and differences between them to help me kind of pick out which one it is and what I should use in order to go along with the reaction. So I really hope this video helped you out. Thank you.